Hello students. So in the previous class we have derived two important derivations and we have found the value of magnetic field B in two different cases, right? So today one more case where we are studying the magnetic field at any point on the axis of a solenoid. Okay, so I said you in the last class only solenoid is nothing but it is a wire, it is a electric wire bounded in terms of several turns. Okay, where we are generating magnetic field. Okay, so let's find the magnetic field B at any point on the axis of a solenoid. Okay, so now I'll draw a solenoid first. Okay, so let consider here one solenoid, somewhat of this kind. Okay, so now let L represents the length of the solenoid. L is the length of the solenoid and N is what? Total number of turns. Means I said you will be having a turn of wires. Okay, so N is the total number of turns in its winding. Okay, now the number of turns per unit length, the number of turns is nothing but N. Number of turns is N. So the number of turns per unit length is N divided by L. Because if this is one solenoid, so around it we are having different windings of a wire in several turns. N number of turns. So N by L is what? Total number of turns per unit length. Okay na? So this is axis of the solenoid. At the middle we are having the axis of the solenoid, right? So this is what? Axis of the solenoid. So let's consider A as this length is what? A, and what this A represents is, it's nothing but radius of the solenoid, right? But because this is the axis of the solenoid and A is the radius of the solenoid. Okay, so now a current of amount I is flowing in the solenoid. Okay, so this solenoid contains air in its core. So this solenoid containing air in its core. Okay, so now in such case means this is one solenoid of length L, of the turns N, of the turns per unit length N by L, in which current I is flowing and whose radius is I, and which is containing air in its core. So in this solenoid, let us find the magnetic field B, right? And as you know, we have to consider one fixed point P. So now let's consider P is a fixed point. Okay, so P is any fixed point on the axis of the solenoid. So we have to find the magnetic field B at a point P on the axis of the solenoid, right? So the derivation indicates that only, magnetic field at any point on the axis of the solenoid. Okay, so for that what we have to do, we have done in the previous derivations also. What we have to do, consider one element of such kind. Okay, so this is an elementary length dx of the solenoid. This is elementary, as you consider dl in the first derivation, like that. Okay, so this is the AB is the elementary length. Means first what we'll do, we'll find the magnetic field only in this portion, then we'll apply the same theory for whole solenoid. Okay, so for such derivational part, we have the elementary length dx of the solenoid, which is AB. AB is the elementary length element is the element. AB is one element whose length is dx, and this dx is located at a distance x from P. Okay, P is any point on the axis of the solenoid, and AB is one element. Okay, so this AB is situated at a distance x from P. Okay, now we can regard this element AB as a circular coil of radius A, right? Because this whole solenoid is, means if this is one whole solenoid, it is having so many number of turns of the wire winding like this. Okay, so in that, if you are containing any one element AB, so to that AB you can consider it as it is one circular coil. It is one circular coil, right, of radius A, and which is having the what turns is n dx per L. Because if you consider the whole solenoid, so the total number of turns is what? N divided by L per unit length. So we are considering only AB now. So this AB is one circular coil of radius A, and it is containing n dx divided by L number of turns. Okay, so now write the magnetic field. Now write the value for magnetic field. Magnetic field induction or magnetic field at P due to the element dx will be what? Mu naught I a square divided by 2 n dx divided by L, and 1 divided by a square plus x square plus raised to 3 by 2. Okay, so how this came? From the previous derivations where we found the magnetic field at a circular coil. Okay, so there we done like this, and here there we done n by L, but here it is n dx divided by L. Okay, so now let us use an angle pi here. So what is this angle? So this is the P. Okay, so from P to A I am joining, from P to B also I am joining. Okay na? So from this P to the ends of the solenoid, to the ends of the solenoid also I am joining. Go on writing the derivation. So let's consider this is a C, this is a D. Means the C and D are what? Ends of the solenoids. Okay na? So now let us use the angle pi here. From where? Means from where you have drawn the line from P to B. Okay na? So there you write one angle pi. Okay, and where you have written this A, you have joined P and A na? So there also one angle comes here. To that you call it as D pi. Okay, so then this is X. Okay, and this is pi, means this in this right angle. Okay, you can write X is equal to A cot pi. Okay, apply this here, you can understand. Okay, then write what is dx. What is dx? Means differentiation. Minus A cos x square. Cot x is cos x square. Pi and d pi. Okay, so now substitute these values in equation 1. So what? Because no, here we are writing dB because we are finding only magnetic field in this element AB. So dB value becomes mu naught I a square is same as it is. Okay, so n as it is. Dx value changes here. Minus A is there. Let's write that minus here. A cos x square pi d pi divided by L is as it is. A square plus x square raised to 3 by 2 is there. A value is x value is A cot pi. So here A square as it is. In the place of x square, can I write A square cot square pi? Okay, raised to 3 by 2. Okay, just simplify this term. Simplify this term. A square, take here a square outside, and this a square, that a square get cancels. Okay, so again 1 cosec square is there. So by adjusting all the terms, can you write mu naught in divided by 2l into sin pi d pi. Okay, here also cot square is there. 1 plus cot square terms comes here. Okay, what all the changes you can do, you see. Okay, I hope it is not visible. See here, in this term what happens, a square you can take outside, so 1 plus cot square is remaining, replace that. Cosec square is there, you can cancel, then this a square get cancelled, so you will get this term. Okay, you can understand, no need to explain. Next, so now this is what the magnetic field at P due to only AB, right? So now what we have to find, we have to find magnetic field at P due to the entire solenoid, right? So for that, obviously what we have to do, integration. Minus mu naught in divided by 2l, integration from where, integration from where means, see here I'll denote one angle alpha from this end line to here, and again from this end line to here, this is beta. Better I'll write this like this only. This is one line which is joining P to end point, so their angle is alpha. So this line also is joining P to end point, so their angle is beta. So the entire solenoid is from in this region, no? Alpha to beta, right? So if you find the magnetic field in the range alpha to beta, then you can find the magnetic field at P due to the entire solenoid. Understood? So here what we have to do, these all things remaining constant and sin pi d pi. Now differentiate. Try to understand the physical meaning in the derivation, not only the mathematical part. That mathematical part you can understand by your own, no problem in that. But try to understand what is happening over there in terms of physics. Not only go for the mathematical steps, because that's why I'm not explaining them much. Okay, so this is what the magnetic field at P due to the entire solenoid. So this magnetic field's direction, this magnetic field at P due to the entire solenoid, its direction is parallel to the axis of the solenoid. This is axis of the solenoid now. So the magnetic field's direction is also parallel to the axis of the solenoid. Understood? So this is magnetic field at P due to the axis due to the point P on the axis of the solenoid, mu naught in divided by 2l into cos alpha minus cos beta. Understood? Here mu, what is mu, what is all those things, you know it. Mu is nothing but one constant. I is the current, n is the number of turns, l is the length of the solenoid. Understood? So this is the, or also you can replace this mu, because mu is equal to mu naught into mu r, relative permeability into absolute permeability, no problem. Okay, otherwise you can write it as it is. So this is what magnetic field at a point, magnetic field at a point on the axis of a solenoid. Understood? This is the point P, and that point P is on the axis of the solenoid. So this is B is the, this expression gives us the magnetic field at this point on the axis of the solenoid. Understood? So this is the one more derivation. So here we complete totally 3 derivations. Okay. Now we have to learn about one more important part, that is Helmu's tangent galvanometer. Okay, before going to that, let me tell you some things you studied in your PUC classes, like you considered one circular coil of radius of some radius, and it was having some what current flowing through it, or the axis means somewhat of this kind. If this is one circular coil, center point, radius, axis, okay, axial line you called it as. Okay, such situations you dealt in the PUC classes. So somewhat of that kind, one about one instrument I can say we are studying over here. You are doing a practical also, maybe depending on the Helmholtz tangent galvanometer. I don't know if it is there for your syllabus or not, but the practical will be there regarding Helmholtz tangent galvanometer. So here let us study about it theoretically first. Helmholtz tangent galvanometer. Okay, so what is this? What is this Helmholtz tangent galvanometer consisting of? Okay, so as I told you, it is consisting of two coils of such kind. Two coils. It is consisting of two coils. That two coaxial coils. Coaxial coils means what? The both the coils are having, let this C1 is one coil and C2 is one coil, so both the coils are having the same axis. That's why they are calling, they we can call them as the coaxial coils. So this is the axis of the both the coils. Okay, I hope it is visible. Yes, no? Okay, so C1 and C2 are the two parallel coaxial coils having the radius A. Both are having the same radius. A. A is the radius. Okay, and the number of turns in the coil is also same, N, for both the coils. Okay, so the distance between these two coils is equal to the radius of each of the coils. So this radius A means I have drawn some far away, but you just think that this distance whatever it will be there, no, it will be same, means distance between both the coils is same as their radius, because each of them are having the same radius. So these coils are connected in series, so that why they are connected in series, because the current through them is in the same direction. Like consider if I is the current flowing through them, so in this direction the current I is flowing here, and here also in this direction current I is flowing. So in between these two pairs, what we have here, the midpoint P, which is very important. Okay, so at the middle point we are having the point P. Okay, so now this is the situation we are having, two coaxial parallel coils of the same radius, and current I is flowing through them in the same direction. N is the number of turns, and distance between them is equal to their radius. This is the situation. So now what we have is the field B1 due to the one coil, means the magnetic field due to the C1 coil is B1. Magnetic field at P due to this coil is B1, and magnetic field at P due to this coil is what? B2. So I'll just try to convey about the magnetic fields to you, like okay, so if this is the coil C1 and if this is the coil C2, okay, so this magnetic field is increasing like this. Okay, same happens here also. Okay, so this is the magnetic field B1, increasing and magnetic field B2. How these B2 and B1 changes, I'll tell you. Okay, so here the field B1, due to the first coil is decreasing linearly with x, means like this. If it goes first, but it is decreasing linearly. Okay, while this b2 due to the this coil is increasing linearly, right? I'm talking about the center. Okay, so at the center, at the middle point, what is happening? The magnetic field b1 due to the one coil is decreasing linearly. Okay, and the magnetic field due to the second coil is increasing linearly. Okay, so if we add up b1 and b2 to produce the field, which is as b1 plus b2, which we can call it as the resultant field. Okay, which we can call it as the resultant field. So at this point, we can find the resultant field b1 and b2. So for that, what I will do, at this point we will keep one here. At the point P, we will keep one compass box X. One compass box is placed at the P, the midway between these two coils. Hence, the magnetic field in which magnet is situated is uniform. Means from this coil also, whatever the magnetic field is there, which is linearly decreasing, and from this coil also, which is linearly increasing, whatever the amount of decreases here, the same amount increases here. So the noted magnetic field at this magnet is uniform, right? So now in such situation, we have to find the magnetic field. Okay, see here. So I hope you can remember this. Okay, I'll just now go on writing the things. Okay, so this is about what construction of the Helmholtz galvanometer. So what theory of the Helmholtz tangent galvanometer explains is, if the rate of variation of field at this point P, if the rate of variation of the field due to the coil, due to any coil, means by this coil also or by this coil also, it should be constant. That means theory tells that the rate of change of magnetic field at this point should be constant. It may be decreasing or it may be increasing. So the theory of Helmholtz galvanometer tells us that the rate of rate of changing of the magnetic field, that is dB by dx, that should be constant. So if dB by dx is constant, then d square b by dx square is 0, right? So you know already what is the magnetic field for such coil. What is the magnetic field at any point due to the coil? You have already derived it. What is that? B is equal to mu naught n I a square divided by 2 into a square plus x square raised to 3 by 2. This we are already derived. Magnetic field at any point due to a circular coil. Okay, now differentiate it. dB. Okay, so mu naught n I a square remains as it is. You just have to okay, you just have to differentiate the things here. 2 is a square plus x square raised to 3 by 2. Okay, so that is a square plus x square raised to minus 5 by 2, and it's 3x. Okay na? So now again differentiate d square b by dx square. And it is minus 5 by 2, means it is minus here. Okay, right? No, mu naught n I square divided by 2 square plus x square I square 2x minus. Okay, this is the first derivation. dB means dB by dx. Again differentiate one more time. So what we will get? Mu naught n I a square as it is 2, and a square plus x square raised to minus 5 by 2, okay, plus product rule. x minus 5 by 2 a square plus x square raised to minus 7 by 2 into 2x. Okay, you can differentiate, no problem. Again minus. So just simplify the terms now. So what it comes is a square plus x square raised to. So I'll write it directly, minus 3 mu naught n I a square. You just simplify the terms. Okay, if you got any problem, ask me. I'm writing the steps directly. You can get the same thing if you solve. Okay, so now what is the d square b by dx square we obtained is this. Okay, so now what we told in the initial, the theory of the Helmholtz galvanometer told us that the rate of change of magnetic field is constant, hence d square by dx square is 0. So if you want d square b by dx square is 0, when this can become 0, if this can become 0, if a square minus 4x square is 0, if a square minus 4x square is 0, then d square b by dx square also equal to 0. So what this a square minus 4x square equal to 0 is nothing but what? X equal to plus or minus a by 2, right? So the resultant field at the midpoint, the resultant magnetic field B1 plus B2 at this midpoint O due to both the coils is nothing but B is equal to, is nothing but, okay, is nothing but B is equal to 2 into 2 into, because two coils are there, mu naught Ni a square divided by 2, 1 divided by a square plus, in the place of x what we have to do, a by 2, a by 2 square raised to 3 by 2, because x value are written no, plus or minus a by 2. Because you already know the circular coil, in the case of circular coil magnetic field will be what, mu naught Ni a square divided by 2, 1 divided by a square plus x square 3 by 2, but here we are having two coils, hence 2 into, and here in this case x value is a by 2, hence we have written this. Again if you simplify this, you will get b is equal to what, 8 mu naught Ni divided by 5 root 5a. Okay, I have not gone in every step in detail. You solve it by your own. Okay, na? So this is what the magnetic field at the midpoint due to both the coils. Understood? So now, as I told you, in these two coils current is flowing. So if in order to find the unknown current, what we have to do, how to find the current flowing in this is what you have found, the magnetic field. So if you want to find the current here in this situation, what is the value of I, if you want to find, so what we have to do means, these two coils means now they are in the plane of the paper. Okay, these two coils are lying in the plane of the paper. So what we have to do, you have to make the planes of the coils are lying in the magnetic meridian, BH tan theta, you know it. Okay, you have to make these two coils to lie in the plane of magnetic meridian. So at that time, if theta is the deflection of the needle, then what we'll get, 8 mu naught, whatever you obtained here, no, 8 mu naught Ni, okay, whatever you are obtained here, Ni divided by 5 root 5a, that is equal to BH tan theta, because we are making the coils to lie in the plane of magnetic meridian. So what this BH is nothing but, it is nothing but horizontal component of the magnetic field. BH is the horizontal component of magnetic field due to Earth's magnetic field. You have learned this in the PUC classes only. So hence I value we can obtain it as, send all the terms here, 5 root 5a BH tan theta divided by 8 mu naught n. Okay, now these all terms, let's call it as a one constant k, tan theta. So this is what the value of current flowing in these two coils. So for that, what we done, we made the coils to lie in the plane of magnetic meridian. So hence we got here BH tan theta. Theta is nothing but what? It is the deflection of the magnetic needle, and BH is the horizontal component of the magnetic field due to Earth's magnetic field. So all these things comes like this. So I is equal to K tan theta is the current flowing in the Helmu's tangent galvanometer, and this B is the magnetic field at the middle point due to both the coils. Understood? I hope you have understood these two concepts which are discussed in today's class. So if you got any problem, ask me. Okay, I have not gone very much detail. I have not went into the detail because the steps you can solve by yourself. Okay, so if, but before, means solving the steps is also important, but I refer more to understand what is physics behind every step. Why you are taking this step only, why you are taking this step only, why the terms changes in this manner. Okay, substitution and simplification, you can do it, no worry about that, but try to understand the physics over there, try to understand the exact phenomena happening over there. Okay na? So in this way, try to understand the theory explained today. So the remaining things we can discuss in the next class. So with this, today magnetostatics part completes almost. Okay, so we'll switch on to the next part of the chapter in upcoming class. Okay, thank you. Ask me if you have any doubts. Okay, thank you.